So here we are, Chem 203, lab number 9, osmosis and dialysis. Osmosis and dialysis, they might seem like different things, but they're really closely related. And we're going to find out how they're related in the process of performing this lab. It may seem complicated. What you'll need to do, of course, is go to Blackboard and download the hard copy, which will give you details on the experiment itself, which I will summarize as we go along, but I'm not going to go through every little detail that comes up. Okay, so hold on, let me share the screen. And right, this is what the what is that one doing there? All right, this is the osmosis and dialysis lab here. Right. So there's a lot of introductory material, and I'll go through that in just a few minutes. And then we get to the steps of the procedure. Here for osmosis, here for dialysis. Right. And then post-lab. Here goes the data sheet, right? I'll give you the data that you would have collected had you done this hands-on, and that's over in this other screen. The data that you would have collected. This is fairly reliable data. It was acquired about a year ago by one of the former class participants in Chem 203. Okay, so you'll get both of these, download and print this lab sheet off, the lab, the hard copy lab. And then this is one sheet, the data sheet, will give you all the information that you need to answer these post-lab questions. All right. Now the pre-lab questions here at the bottom, we'll go over those, and it's almost as if I'm giving them to you. So you'll get these points for free. You'll also get the lab points for free because you don't have to actually perform the lab. So you're starting off pretty well off to begin with all that data. And the real test will be, can you answer these post-lab questions? All right. Okay, so let me take back the screen so I can use my whiteboard. And let's start off with objectives. I mentioned before that we're going to look at osmosis and dialysis. So what is osmosis? Right? We need a definition of what these things mean. Right? Osmosis requires two solutions. Right? And these solutions are separated by a membrane, which means some things can pass through it. This particular type of membrane is semi-permeable. All right, so there's a semi-permeable membrane. On one side you have a solution, and on the other side you have a solution. Now the nature of this membrane is such that the only thing that can pass through it is water, or any molecules that are smaller than water. So most of the gases will pass through without any trouble. But since water is the only thing that can go through, and the membrane is constructed also so that it will not allow ions to pass through. There are a whole host of different types of membranes that are available. And what the semi-permeable membrane tries to do is mimic the cell membrane. So, what happens with that solution? Well, water can pass either this way or that way. And we have to talk about why it wants to go one way or the other in just a couple of minutes. But since we're dealing with definitions, I'm going to stop there and let that stand until we actually get into some more details. All right, so the other part of this experiment is dialysis. All right. Right, so dialysis is a process that has two solutions, one on either side of a membrane. But this membrane is differentially permeable. Sometimes the word is used, this is what the authors of the method use, differentially. Sometimes you'll see, rather than differential, you'll see selectively. Selectively permeable. So the basic difference between the semi-permeable and the differentially permeable membrane is a difference in pore size. Right? The pore size of the differentially permeable membrane is just a little bit bigger than the pore size for the semi-permeable. And what that allows is for the solution on either side, and for all intents and purposes, we're talking about aqueous solutions. This membrane allows water freely to move back and forth. There's really no selective pressure forcing water to go one way or the other. But since the pore sizes are larger, it's not just water that can pass through, but some molecules that are larger than water, like urea. Right? That's a good one because dialysis is used to help people who have kidney failure rid their bodies of nitrogen waste, which in humans and mammals takes the form of urea. Right? So water's like this. Right? That's a certain size molecule. Urea is bigger. Right? So urea is considerably bigger than water. But it may pass through the membrane. Now, even a bigger molecule will also pass. Glucose will also pass through that membrane. So there is selective pressure driving the molecules this size to go through the membrane, and it depends on the concentration gradient across the membrane. If the glucose concentration is higher on this side, it'll want to go that way. So if the urea concentration is higher on this side, it'll want to go that way. But other molecules will not pass through the membrane because the pore size is too big. Things like proteins or polymers of some kind, other kinds, proteins of polymer, like starches. Right? And then we're going to use a starch in our experiment to demonstrate this model. We'll also use glucose in the experiment as well. Okay. So those two definitions. Now we need some other definitions. Well, I've been using the word solution because I know we've gone over solution in class. What is a solution? Solution is a homogeneous mixture. Right. All right, that's one. And it's composed of at least two components. Right? There's the solvent, which nearly always is the major component, or at least in the beginning when you're making a solution, it is the major component. But depending on the solubility of the solute, you may get to the point where you have more solute than solid. But when we started out with low solute, high solvent concentration. So they retain those names even if the solute is more concentrated. Good example, sugar water. Right? Sugar, sucrose is extremely soluble, very high solubility in water. And you can make concentrated solutions of sugar have much more sucrose in the water. But we have a solvent, we have at least one solute, and many times, for example, in blood plasma, you have lots of different types of solutes. They may include the wastes, like ammonia, and excess glucose, especially for diabetics. They have various types of protein. The most common one is albumin. And there are some other polymers that we won't go into right now. Okay. So there's one other term that we need to understand when we talk about osmosis and dialysis for that matter. And that term is called tonicity. Tonicity describes the tendency of a solvent to cross the semipermeable membrane for an osmotic process. Right? What tendency is that? The tonicity pushes the solvent, water, across the membrane. Right? And our model is the cell. Okay, so there's more to tonicity than just the definition. Right? We still have a membrane, and we still have a solution, one on either side. Let's say this is the cell solution. This is inside the cell. This is outside the cell with the cell membrane in between. Now, for those of you who have had maybe even a biology course, but certainly anatomy and physiology, you understand that there are two basic ways to move things across the cell membrane. One is passively, and that depends on concentration of that component on either side of the cell membrane. The other way is active transport. And we're not going to talk about active transport. This is just passive movement. So in this case, passive movement has to do with water. That's for osmosis. Right? And it has to do with the concentration So if you think about the concentration difference with respect to the cell, then the definitions make more sense. Okay? So if the concentration on this side, and I use square brackets from chemistry, of course, means is a way of saying concentration. Actually, it's equilibrium concentration. But it's a shorthand, right? So the concentration of your, let's do it this way. Let's not use that because we reserve that for equilibrium. Let's just say the concentration of the solute on that side and that side are equal. All right? So we got the same concentration on both sides and they're aqueous. Right? So you got the same amount of solute, you got the same amount of water per milliliter. We say this solution, and this is the easiest one to understand, is isotonic. Okay? Iso is the Greek prefix for same. Right? I don't know about you, but as a little kid, I played around with these little invertebrates. We used to call them roly-polies, right? Because if they were walking and you reached up and touched them, they'd roll up into a ball. That was a defense mechanism. But if you let them walk, then you could look at their little legs. All of their legs are exactly alike. They're same legs. So biologically, they're called isopods, same foot. Pod is the Greek for foot. So this is same tonicity, right? And relative to the solute in this solution, it is the same tonicity as that one. Okay, so it's isotonic. Now what happens if across that membrane the concentration of solute on this side is greater than on that side? Right? So the higher concentration of solute, not solvent, solute, on this side is higher than on that side. We say relative to this one, that solution is hypertonic. Right? It's a hypertonic solution because relative to the cell, it has a higher solute concentration. Right? So what does that mean? Well, if the solute concentration is higher here, how is the water concentration related? Right? If this one goes up, the water concentration has to go down, right? Because you're taking the place with solute of the water molecules. So the water concentration on this side has to be less than the water concentration on that side. Now that you know that, a hypertonic solution says that the gradient for water, since it's the only thing that can move across the membrane, the gradient for water drives it this way. So a hypertonic solution will cause water to move out of the cell into the solution surrounding the cell. And what happens to the cell? It shrinks, right? Because you're taking volume out of that cell. It shrinks, it loses mass, and if you go far enough, it'll die. Right. The other possibility, we've talked about isotonic, hypertonic. Now, if the concentration of solute inside the cell is greater than the concentration outside the cell, we say now that this solution is hypotonic. Hypo meaning beneath, less than the tonicity. So this is less tonic than that one. Okay? So that means that the water concentration on this side is less than on that side. Okay? So for hypotonic solutions, the pressure for water is to move into the cell because it has a higher concentration outside than inside. And you may often hear in discussions of movements of atoms and molecules, the water follows a concentration gradient. In other words, it moves from a place of high concentration to low concentration. That's what's happening. Only with the membrane, that movement is restricted. It's only allowed for water in the case of osmosis, right? So, for isotonic solutions, water moves no direction. It doesn't move at all. And those are the kind of solutions that healthcare professionals need to deliver in an IV to the patient, because an isotonic solution will not damage cells. Right? So lactated Ringer solution, for instance, is isotonic with your blood and consequently with body fluids. Right? So it doesn't damage your cells, but it provides some nutrients and fluids. Okay, so we know about tonicity, we know about isotonic, hypertonic, and hypotonic, and which way water moves across a semi-permeable membrane. All right. Let's see. All right. Let me share this one screen and just illustrate tonicity. Well, I thought I had it pulled up. It's going to take too much time to get it. We've already described it anyway. The way cells are and how they behave in an isotonic, a hypertonic, and hypotonic solution. Right, so let's move on, because this is going to take a while if I just keep rambling. Okay. Now, we talked about dialysis. Let's go back to osmosis. How are we going to study osmosis in the lab? Right? So for the osmosis part of the lab, we're going to use potato plugs. Right? So we take, I don't know if you've seen or not, but a cork borer is a device that has a defined diameter, and if you need a hole in your cork before you stick it in a test tube or a flask, then you take this thing and bore a hole through it. Right? So we're going to use one of those and just bore into an Irish potato, probably a russet. And then there's a little it's got a sharp end, so we bore into our potato, take a plug out, and then we stick a long thin rod down there and push the plug out, right? And then we cut off a piece of about 40 millimeters or thereabouts. And those pieces you towel dry. You don't put them in the towel and suck all the water out of them. You just make sure that they're dry to the touch, and you measure the length, measure the mass, and then we do our experiment. And you'll need 3 of those, right? Because we're going to have 3 different solutions. We're going to have one that's isotonic, one hypertonic, one hypotonic. And the cell membranes of the potato cells will serve as our diagram before, with the cell on one side and the external solution on the other. And then after so many minutes, whatever the lab calls for, you remove your plug of potato and towel dry it, and then you make observations. You make visual observations and physical observations beforehand and then after. You know, did it get limp? Did it get stiff? Did it get really hard? And then you take the same types of measurements. Do the mass, do the length, and compare them with the original results. And draw some conclusions. That's what the post-lab questions are about. Okay, so that's how we're going to study osmosis. Right. Dialysis Dialysis is best described in terms of the process called hemodialysis. Right? We know what dialysis is. Hemodialysis is uses blood as the it's the hypertonic side of the waste products. Right? So since the membrane in dialysis is differentially permeable, it will allow water freely moves back and forth. So what we do is we make sure that the membrane separates the what we call the dialysate solution, and this one is normally an isotonic. It's isotonic to body fluids for every component except the waste products you want to remove. Right? So now we're talking about tonicity in terms of multiple components. Right? So it's isotonic with respect to let's see, any of the ions, right, that they identify as electrolytes. So the electrolyte concentration is the same on both sides. And over here is blood. It's continuously flowing through a tube that is a differentially permeable membrane. Right? So since water moves back and forth, and they're both isotonic, things like water, electrolytes, various other components. And the only difference is the difference in waste products, right? There's no urea over here. There's no glucose over here. And whatever other waste products that your body normally develops, those are just a couple. And then you have lots of urea over here for a patient whose kidneys are failing. They cannot get rid of the urea. Right? And they tend to build up glucose as well. So these are hypertonic with respect to waste products. So they tend to move that way. And they effectively clean the blood of those waste products. Now, unfortunately, most patients have to have this process repeated 2 or 3 times a week. Right? That's how fast the waste products build up in your body. So it's not a pleasant experience, I'm told, because it takes 2 or 3 hours to do it. Right? So you spend a lot of your time And I would assume that most of them are waiting on kidney transplants. So this is hemodialysis. Now this membrane is our differentially permeable membrane, and in our experiment we're going to actually use the same type of tubing in our experiment as is used in the dialysis labs. Right? It's called dialysis tubing. It comes in a flat roll, and it has low moisture. I mean, it's not bone dry, but it's very low moisture. And before you use it, you have to hydrate it, right? So I would have cut off pieces about that long and submerge them in distilled water and just let them hydrate. And then you take out a piece and you use a glass rod, is the best because it has no sharp edges, and find out how to open up the tubing, right? Because it's flat to start with, but it's really 2 layers. So you open it up, and then you, some teaching labs have available these clips that you can put on it. You just fold it over a couple of times and put a clip on it, and that seals off one end. We don't have that luxury. So we're going to take a string and just tie off one end, right? And then you're going to fill it up with a solution of glucose and then a solution of starch, right? 2 different size molecules. Glucose molecule is a lot smaller. Starch molecules are huge. And then once you get it in there, then you tie off the other end with a string or a rubber band, and then you submerge it in distilled water, I believe. And you leave it there for a while. Then you test the solution, right? You want to find out what actually moved across the membrane, right? So if we have this dialysis tubing, which is like that, and it's tied off at both ends, and it has, let's see, I think it's, looking for the percentages, 20%, no, that's not right, 0.25% starch, about half of it is that, and then the other half of it is 10% glucose. Right? And then you put it in your container with distilled water. Right? So, which way would you normally expect these things to move? Right? If the membrane is permeable to both of them, then of course distilled water out here would be hypotonic to the contents inside the tubing, and they would move out into the water, right? Okay. But if it's not permeable to both of them, then one of them's going to move out into the water, and the other one's not going to move. So you need a way to test it. Okay. So, there's a test for each of them. Right? I might as well talk about it now. This is sort of stream of consciousness education. So, in order to test for glucose, now let's do starch first. That's easier. To test for starch, we use a solution of potassium iodide. No, just one. Potassium iodide. and elemental iodide in solution. Okay? I'm not going to talk about the chemistry right now, but what happens is when you add that to a solution, if there's any starch, and it's extremely sensitive, very low concentrations of starch, what happens is you develop a blue to purple, sometimes a very dark purple color. Right? So it's very specific for starch. So if you've got any starch out here in that solution, when you test it, it's going to turn blue-purple. Right? If you don't, you won't see any change in color. For glucose, there's another solution called Benedict's. Benedict solution. Now, chemistry there is a little complex too, but at the core of the chemistry is copper. Right? So copper 2+ ion is in solution here, which means it's combined with water is going to give you a blue color. Now, if there's any glucose in there, and the reaction doesn't happen very fast at room temperature, so we need a boiling water bath. So when you develop this test in the solution looking for glucose, you have to put it in a hot water bath. And when you do that, what happens is the glucose causes this copper to be reduced, which means we add an electron to it. So now we have copper 1+. We just add one electron to it. And what happens is, under these circumstances, copper combines with oxygen and precipitates as an orange, sometimes a brick red color. And the range of color gives you a semi-quantitative indicator of concentration. Right? So if it's very low concentration, it should be, let's see, maybe even only green. It goes from blue to green, to yellow, to orange, and then to red if it's a very high concentration. So the chemistry here is a little complicated, but any type of sugar that can cause this to happen, call it a reducing sugar, can cause copper to reduce from that to that, from 2+ to 1+, will give you a positive result. So we could use other sugars than glucose, but since glucose is physiologically important sugar, it makes sense, right, for chemists to give a head nod to physiology. Right? So that's going to be our dialysis test using this dialysis tubing. Okay, so read the method and you'll get more details about that process. Now let's move to our pre-lab questions. Okay, I'm going to erase this so we have more room. We need more room. All right. So now we have some pre-lab questions. Let's go over them. Okay, question number 1. Calculate the amount of sodium chloride needed to prepare 50 milliliters of 2 different solutions. First solution, 0.9% sodium chloride. And the other one is 20% sodium chloride. Now these are going to be aqueous, of course. So we want to know how much sodium chloride is required to make 50 milliliters of that solution. So the total volume for both of them is going to be 50 milliliters. Right? Now, as I've said in class before, the problem with percent is it's a dimensionless number. It's just parts per hundred. So what does it mean? What kind of parts to what kind of hundred? I mean, is it grams per 100 grams, which would be mass? Is it grams per milliliter? Or is it milliliters per 100 milliliters? Right? Those are the possibilities. Well, in this case, we're going to assume that what we're talking about in 0.9% sodium chloride is mass per volume. So we're going to say this actually means 0.9 grams of sodium chloride per 100 milliliters of solution. Okay? So that makes it pretty simple, right? If you only need 50 milliliters of that, how many grams of sodium chloride do you need? Right? Half, right? This is half of that. So the ratio says you only need half of that. So the answer is 0.45 grams sodium chloride for that solution. Now, why did we pick 0.9% sodium chloride? Well, 0.9% sodium chloride is isotonic with most mammalian cells. Isotonic with your body fluids. So it should be isotonic, and probably is. We would expect it to be isotonic with potato cells too. So this is going to be our isotonic solution. What about 20% sodium chloride? Right, there's a whole lot more sodium chloride. So relative to the cell, which way are we going? The solute is going up, which means hypertonic. So this is our hypertonic solution. Now we need to know how much sodium chloride we need to put in 50 milliliters. Well, if we use this ratio again, it would be 20 grams sodium chloride per 100 grams of solution. Excuse me. Well, technically that's pretty close, but it's 100 milliliters of solution. Okay, so now if we only need 50 milliliters of this solution, how much sodium chloride do you need? Half. So you need 10 grams. Right? So you need 0.45 grams here, 10 grams here, in 50 milliliters of solution. Okay, that's our hypertonic. So that's our isotonic, hypertonic. What's our hypotonic solution? The one that has lower concentration of solutes than in the potato cell. We're going to use distilled water. I mean, that's as hypotonic as you can get, right? Because there's nothing there but water. Right? So pure water is our hypotonic solution. Okay, those are our three solutions. Now, PreLab question. PreLab question 1 didn't mention this one. right? Because you don't have to do anything to prepare that one. Right? It's right out of the bottle. So we'll move on to 2. Pre-lab question number 2. Right. Briefly explain the following. A. Isotonic solution. Right. How would you define an isotonic solution? Well, remember, when you're defining these solutions, you always have to compare them with something else. And the assumption is that we're comparing these solutions to living cells. That's the predominance of meaning for tonicity relative to a living cell. So with that being said, although it's not absolute, I mean, you can refer to a difference in tonicity between this solution and that solution, and it doesn't matter what the solution is. So if the concentration of solute in this solution is the same as our solution of interest, right, defined here, then you would say this solution is isotonic with that solution. Okay? So you're saying that when the solutions are compared, the solute concentrations are equal. Okay? I'm not going to write that up there because you have ears. And if all goes well, I'll have this video closed captioned. Hypotonic. Oops. I can't spell. Hypotonic solution. This solution, as compared to the other solution, is lower concentration of solute. Hypo. Lower concentration of solute than the one compared. And then the last one you probably guess is hypertonic. So the hypertonic solution has a higher concentration of solute than the comparison solution, or the cell. Okay? So that's 2. Question number 3. Okay? Describe the function of dialysis tubing. Well, what is the function of dialysis tubing? Well, dialysis tubing, as a differentially permeable membrane, allows water and some larger molecules than water to pass through the membrane. But larger molecules are prevented from passing. Usually also it prevents charged molecules from passing. So what is it used for? Well, most commonly it's used for cleansing a patient's blood of waste products, such as glucose and urea, because their kidneys will not do it for them. Okay. 4. What's the purpose of Benedict's solution? In other words, what is Benedict's solution used for? I mean, I just described it to you, so you should be able to answer that one. Benedict's solution detects the presence, in our case, of glucose. It actually detects any reducing sugar, right? But we're not going to define that any further than the fact that those types of sugars are capable of changing copper 2+ to copper 1+. Right? They are the reducing agent. The sugar, the reducing sugar, is the reducing agent. Okay. Now, what's the purpose of the iodine test? The iodine test is used to detect the presence of starch. Right? I remember when I was a kid and starting to get interested in the sciences, one of the uses of the iodine test that my teacher would put it to would be to show how well, actually, they didn't get this complicated. They were testing for starches, right? So if you test a, I think they used a cracker. Test a cracker, just put a drop of this iodine solution on it, and it turns almost black. Right? There's lots of starch in the cracker. But crackers, saltine crackers, don't have any sugar added to them. At least they're not supposed to. So you're testing, you're getting starch. If they had used the Benedict test then, they probably would have found no sugar, no reducing sugars, no glucose in that cracker. But they had us put cracker in our mouth and chew it. And it started to taste sweet. Right? Where did that sweetness come from? Right? We know sugars are sweet. Starch is not sweet. Right? If you've ever taken some cornstarch and put it on your tongue, initially it doesn't taste sweet. Right? It's just yucky. Bad mouthfeel. But where does the sweetness come from? Well, that doesn't have anything to do with our test today. I'll just say what happens is there's an enzyme in your saliva called amylase. And what it does is it takes starch and breaks it apart in individual glucose molecules. Right? And then you taste sweet. But initially, we knew that that sweetness had come from starch because we tested to be sure that there was starch there. Okay, so the iodine test is used for testing the presence of starch. So that's the last of your pre-lab questions. You can fill those out in your own words. You'll want to do that because these are easy points. I just gave you all the answers. Only a fool would throw away points, right? Right. Okay, so what do we have left to discuss? Well, oh, okay, here we go. So just to recap, the experiment's going to come in 2 phases, right? We're going to demonstrate osmosis with potato plugs in 3 different types of solution. 1 hypotonic, 1 hypertonic, and 1 isotonic. Right? You're going to get observations that you can get from the provided data set and you need to fill out your own data set, I mean, just put the numbers there. But pay attention to what you're putting in the data set for your copy of this experiment, right? Because there are going to be some post-lab questions that are asked, and you need to reference the data to know how to answer those questions, right? So don't just copy it over. I mean, don't just be like a medieval monk copying a manuscript, right? Pay attention to what you're copying and what you should be doing, or what you would have been doing hands-on in the lab, to get that information and put it in your table. If you do it that way, and you know the method that you're doing while you're gathering the data, your observations, both quantitative and qualitative, then when the post-lab questions come around, you won't sit there saying, duh, right? You'll be able to answer the questions because you were thinking about the data at the time you were putting it in your table. All right. So that's our osmosis and dialysis lab. You need to, before you, well, it's kind of late to say that, but you need the hard copy of the data set and the lab, and this video will be uploaded sometime on the day that you're supposed to start the lab. And I'm not thinking of anything else that needs to be provided for you. I think you've got everything you need to do this lab. Word about safety. We always need to talk about safety in the lab. What are some things that could go wrong safety-wise? Well, you've got a hot water bath, right? A boiling water bath, right? So you could scald yourself. So you got to be careful there. We've got 2 reactive solutions, iodine. You spill some iodine on you, and you'll see some purple spots on your skin, right? Because all your cells, well, there's a little bit of starch in there, not a lot, but animal starch, they call it, will still react with iodine and give you the purple color. There's a lot of animal starch in your liver, but hopefully you won't get that close with this solution. Benedict solution, right? It's reactive also. And then, of course, there's glassware that could break. So you want to protect your eyes. If you were doing this lab hand-on, you would have your goggles, eye protection of some kind. You would have disposable gloves. You would have your lab coat. You would have closed-toed shoes, right? No sandals, no open-toed shoes. This is not a fashion show. And it's not a summer walk on the beach either. And of course, any of your leg that's exposed below the lab coat needs to be covered in some form of fashion. Hosiery, tall socks, long pants, whatever it takes. So those are the safety concerns, and any others that you can think of would prove that you're actually thinking when you're doing the lab. Okay, I believe that covers everything. So, I gave you all this information, give you this video, now you're on your own. Finish the lab, turn it in for a good grade.